Imagine, for a moment, that the second planet from the Sun has a secret. Not on its surface, where temperatures melt Laird and the atmosphere crushes anything we send with the weight of a deep ocean. Below, under the rock, under the basalt plains, in the cold, stable layers that the old Soviet landers never reached and the modern orbiters have only just begun to probe. Now imagine that a new pattern recognition model, fed decades of radar data from Magellan, Venera, and more recent missions, has started to draw lines on a map of Venus that nobody drew before. Straight lines, repeating grids, structures that, in the language of planetary geology, should not exist. That is, at least, how the story is circulating. A detailed AI survey of Venus's subsurface has reportedly identified geometric anomalies that some observers are calling the signatures of ancient cities, still intact, preserved in the relative calm of the planet's deeper crust. It is a dramatic claim. It is also, for anyone paying careful attention, a claim that needs to be unpacked slowly, because what the data actually shows and what the headlines have turned it into are not the same thing. Let us start with what we know about Venus, because most of us know very little. The planet is nearly Earth's twin in size and mass. It orbits the Sun at about 70% of Earth's distance, and yet its surface is one of the most hostile environments in the solar system. Temperatures average around 460 degrees Celsius. Atmospheric pressure at ground level is 92 times that of Earth, the equivalent of sitting at the bottom of a kilometer of ocean water. The atmosphere is primarily carbon dioxide, wrapped in high-altitude clouds of sulfuric acid. No spacecraft has survived on the surface for longer than about 2 hours. The last one to try was the Soviet Venera 13 lander in 1982. It returned a handful of color photos, some soil data, and then it died, as planned, in the heat. Because direct imaging is so difficult, most of what we know about Venus's surface comes from radar. In the early 1990s, NASA's Magellan orbiter mapped almost the entire planet, using synthetic aperture radar, which can see through the thick cloud layer. Those maps showed volcanoes, lava plains, highland regions, and strange tessellated terrains called tesserae that look, in certain lights, like broken pavement. For 3 decades, those maps have been studied by planetary geologists looking for clues to how Venus evolved, whether it ever had oceans, and why, despite being so similar to Earth in its bones, it became so different in every other way. The new development is that the Magellan data, combined with newer radar from recent mission concepts and with data from observational campaigns using Earth-based planetary radars like Arecibo before its collapse and Goldstone, has been fed into pattern recognition systems capable of detecting features far smaller than the original analysts flagged. These systems do not see the way humans see. They do not care about volcanoes or rift valleys or the big, obvious features that caught the attention of 1990s researchers. They look for repetition. They look for angles that do not appear in natural terrain. They look for features that repeat at a specific scale, in specific orientations, across distances that would rule out random coincidence. And according to several analysts who have run this kind of survey, the results have been striking. There are regions of Venus, particularly in the lowlands east of Aphrodite Terra, and in a less studied belt south of the Ishtar, highlands, where the subsurface radar returns reveal linear features arranged in patterns that, at first glance, resemble street grids. The features are buried. They sit beneath the visible surface, hidden under basalt flows that are estimated to be several 100 million years old. And the spacing is consistent, measured in kilometers, not meters, but consistent. This is the point where honest framing becomes essential, because there is a difference between saying that a pattern resembles a grid and saying it is one. The natural world produces grids all the time. Basalt cools into hexagonal columns. Polygonal terrain forms on icy worlds. Convection patterns in the deep crust can fracture rock into surprisingly regular shapes. Any of these processes, operating on a planet the size of Venus over hundreds of millions of years, can produce geometric features that look designed. Researchers have known this since the 1970s, when Viking first photographed the famous face on Mars. Our brains are wired to see faces and patterns in noise. Machine vision models, trained badly, can inherit that same bias. So the people working on this analysis are careful. The question they are asking is not whether the patterns exist, the patterns are in the data, but whether the distribution of the patterns is consistent with any known natural process. So far, according to the conversations around the work, the answer has been somewhere between maybe and we're not sure yet. Some of the features can be explained by tectonic stress, some by ancient volcanic plumbing, some by the kind of slow crustal deformation that a planet without moving plates can still produce. But a subset, reportedly a small but persistent subset, does not fit cleanly into any of those explanations. Those are the features that keep making people look twice. Here is where the speculative layer begins, and it needs to be labeled clearly as speculation. Some researchers and a much larger number of interested amateurs have pointed to a theory that has been quietly circulating in planetary science for years. The theory, often associated with Dr. David Grinspoon and other astrobiologists who have written about Venus's past, is that the planet may have once been much more Earth-like than it is now. Climate models have suggested that, billions of years ago, Venus may have had liquid water oceans and a temperate surface for stretches of time lasting up to 2 billion years. That is longer than complex life has existed on Earth. It is a long, long window during which Venus, at least in principle, could have hosted something. Whether that something was microbial, complex, or even intelligent, there is no evidence to say. But the window was real. The runaway greenhouse effect that transformed Venus into its current state is believed to have occurred sometime later, perhaps as recently as 700 million years ago, perhaps much earlier. When it happened, it cooked the surface. Any liquid water boiled away and eventually was lost to space. Any structures, organic or otherwise, that sat on the old surface would have been buried under the fresh lava flows that resurfaced the planet during that catastrophic event. From orbit, Venus today looks young, because its surface really is young. But under the new layer is the old one. And the old one, if it existed, has been protected ever since by the very rock that covered it. That is the premise that makes the new subsurface radar survey interesting. If anything existed on Venus's older surface, it would not be visible to the eye. It would only be visible as an echo, a density contrast, a geometric pattern, a shadow in the radar return, from whatever sits beneath the basalt. And that is, broadly, what the AI analysis is reportedly picking up. Now, the skeptical case. Dr. Martha Gilmore, a planetary scientist at Wesleyan University who has spent years studying Venusian tesserae, has long argued that the older terrains on Venus are probably ordinary geology behaving in unfamiliar ways. Tessera regions look like broken tile because the crust has been repeatedly compressed and stretched over enormous timescales, producing fracture patterns that do not resemble anything on Earth. Her point, which applies to this new analysis too, is that Venus is a planet where normal geology can produce abnormal-looking results, simply because we do not have an equivalent reference frame. Every assumption we bring comes from Earth. Venus is not Earth. Its crust is thicker. Its mantle is drier. Its atmosphere interacts with its surface in ways that have no equivalent here. The moment we see a grid, we should ask, first, whether the grid is real in the data, and second, whether our definition of a natural process is wide enough to include it. That is a serious caution, and it deserves to be heard. The history of planetary science is full of geometric anomalies that turned out to be ordinary. Craters that looked artificial until we imaged them at better resolution, canal networks on Mars that vanished with sharper lenses, faces that became eroded hills once the shadows moved. The lesson, over and over, is that the universe is weirder than we expect, and also plainer than we hope. Still, it is worth noting what would actually settle the question. A new orbiter capable of imaging subsurface features at high resolution over long durations in multiple radar bands. Ground-penetrating radar from a lander, if a lander could ever survive long enough to deploy it. Comparison with gravity anomaly data, because a buried void or a buried dense structure produces a measurable gravitational signature. Seismic data, if we ever manage to put a working seismometer on the surface. These are not impossible instruments. NASA's upcoming Veritas mission, if it flies, will carry radar and gravity science payloads that can test some of these claims directly. The European Space Agency's Envision mission, planned for the early 2030s, is even better positioned. Within the next decade, the question may move from speculation to data. Between now and then, the sensible thing to do is hold two possibilities open. The first is that the patterns being flagged are real features of Venus's geology that nobody had the tools to detect before, and that they will turn out to be natural, even if they are strange. That would be a significant scientific finding on its own. Venus's crust would reveal itself as more structured, more organized, and more complex than current models predict. That alone would change how we think about rocky planets. The second possibility, which is the one the headlines prefer, is that some of those features are not natural, that somewhere in the deep radar returns, the echo of something that was once a surface feature, a settlement, a city, a network built by whatever walked or crawled on a wetter, cooler Venus billions of years ago, has survived under the basalt. If that were ever confirmed, it would be among the most consequential discoveries in human history. Not because it would prove life on Venus in any current sense, but because it would prove that life arose on more than one world in this solar system, and did not stay. Most scientists doing this work are, rightly, not making that claim. They are describing patterns, asking questions, and waiting for better data. The gap between interesting anomaly and artificial structure is vast, and every previous time that gap has been crossed in public discourse, it has turned out to be crossed by enthusiasm rather than evidence. What can be said with confidence is that the Venus we assumed we understood, a dead, boring twin that cooked itself and stopped, is turning out to be more interesting than textbooks allow. Its clouds appear to host chemical signatures like phosphine that still have no fully accepted explanation. Its surface appears to have regions of recent volcanism, suggesting the planet is not geologically dead after all. Its crust, according to the latest models, may be pocked with ancient structures that preserved a record of conditions long vanished. Whether those structures are volcanic, tectonic, or something stranger, they are there, they are measurable, and they are beginning to reveal themselves. A century ago, the same sky we stare at was a place of canals and Martian civilizations and jungles on Venus. Most of that turned out to be wrong, but the world replaced those old stories with something quieter and, in its own way, stranger. Planets that were alive once and died. Worlds that had their chance and lost it. Ruins that we can only glimpse by accident. Whether Venus belongs in that category is a question the next decade of missions will begin to answer. Until then, the radar maps are public, the models are running, and the patterns are still there. Straight lines on a planet that has no reason to have them. If those lines are geology, geology is a lot more interesting than we thought. And if they are not, then the story of Venus is going to need a new first chapter. To understand what any future mission could actually confirm, it helps to look at what Venus hides and what it reveals. The planet's cloud deck sits between about 45 and 70 kilometers above the surface. Below that, the atmosphere is relatively clear, but the pressure and temperature make conventional optical imaging pointless. Radar, however, penetrates the clouds easily. Magellan's mapping in the early 1990s achieved a surface resolution of about 100 meters per pixel across 98% of the planet. That sounds good. In practice, it meant that anything smaller than a large building was invisible. An entire city on the scale of ancient Uruk could sit beneath a Magellan pixel and leave no trace. The lack of detection, in other words, has always been a limit of our instruments, not a statement about what is there. The newer radar techniques under development push that resolution significantly. Veritas, NASA's planned Venus emissivity, radio science, INSAR, topography, and spectroscopy mission, is designed to map the surface at a resolution of about 30 meters per pixel, with certain targets imaged at even finer scales. Envision, the European Space Agency's companion concept, includes a subsurface radar sounder that can, in principle, peer several hundred meters beneath the basalt. That is the instrument that would actually answer the question. Not a ground lander. No ground lander has ever survived long enough to deploy such equipment, but an orbiter with a radar sounder, pulsing signals into the rock and listening for returns. Between now and then, the conversation around the existing data continues. Researchers who have been running machine learning surveys on Magellan archives describe the work in careful terms. They talk about feature clustering, anomaly density, spatial, autocorrelation. They avoid the language of cities and civilizations. That restraint is warranted, but the clusters they find are not random. In some regions, the density of aligned linear features exceeds what stochastic models predict by a significant margin. That does not mean artificial. It means unusual. Unusual is where real science begins. The historical context on Venus is also worth revisiting because it shapes how we interpret any new data. For most of the 20th century, Venus was considered possibly habitable. Before the Venera probes began returning data in the 1960s and 1970s, mainstream scientists wrote seriously about the possibility of jungles, swamps, or at least microbial life in the high cloud layers. Carl Sagan, early in his career, published work on Venusian cloud-top chemistry that kept the door open for life. When the surface data finally arrived and the temperatures turned out to be hellish, the field pivoted quickly. Venus became, in the popular imagination, a cautionary tale, a planet that went wrong, a warning about runaway greenhouse effects, a laboratory for what not to let happen to Earth. The possibility that anything had ever lived there was largely shelved. In the last decade, that shelf has been pulled down again. Climate models by researchers at NASA Goddard, most famously work by Michael Way and his colleagues, have reconstructed plausible scenarios in which Venus maintained a temperate surface and liquid, water oceans for hundreds of millions of years, possibly billions. These are simulations, not observations, but they change the question. If Venus really was Earth-like for a long stretch of its history, the search for evidence of that period becomes legitimate science. Not fringe, not speculative in a dismissive sense, mainstream. And if that period ended in a catastrophic resurfacing event, then any surface features from the earlier phase would be precisely where the AI-driven radar surveys are currently pointing, beneath the basalt, in the older crust, preserved by the very disaster that hid them. The phosphine detection is another thread in this larger conversation. In 2020, a team led by Jane Greaves at Cardiff University announced the apparent detection of phosphine gas in Venus's upper cloud layers. Phosphine on Earth is primarily associated with biological processes or with industrial manufacturing. The detection was controversial. Subsequent analyses produced conflicting results. Some groups confirmed the signal. Others argued it was an artifact of data processing. The dust has not fully settled. But the fact that the question is open at all, the question of whether Venus's clouds contain a biosignature, is itself remarkable. A generation ago, the question would have been laughed out of a journal submission. Today, it is in the journals, being fought over. Underneath that atmospheric controversy is the subsurface controversy, which is quieter but equally alive. The two may be connected. If Venus was habitable for a long period and life took hold, then when the surface became uninhabitable, that life would have had only a few places to retreat. The cloud layers are one of them, a band where temperatures and pressures remain survivable. The deep subsurface is another, if liquid water persisted there after the surface dried. A planet that once had life does not necessarily have life everywhere at every time. It can have survivors hiding in narrow bands for longer than the collapse that displaced them. This is the point at which serious researchers pull back and remind everyone that none of this is proven. What is proven is that Venus is strange, that its history is more complex than we used to think, and that our instruments are finally reaching the point where we can start to test stories that used to live entirely in speculation. That is a significant change. It is the change that makes the AI-driven surveys worth running, even if most of their flagged anomalies turn out to be ordinary. There is also the matter of what the subsurface patterns, if genuine, could physically represent. Not every hypothesis requires cities. Some of the features that look grid-like could be the fossilized remnants of large-scale erosion patterns carved by ancient rivers. Venus, if it had oceans, would have had rainfall, and rainfall over hundreds of millions of years produces drainage networks that sometimes look disturbingly organized from above. Old riverbeds on Mars, for example, have sometimes been mistaken for artificial canals, Percival Lowell's famous error of the late 19th century. Venus may have similar features, preserved because the catastrophic resurfacing buried them rather than eroding them further. If the AI is flagging ancient drainage patterns beneath the basalt, that finding alone would be a major contribution to planetary science. It would show that Venus once had liquid water on its surface in quantities large enough to carve landscapes. It would not require anything artificial, and it would still be extraordinary. Other candidate explanations include ancient tectonic fabrics, the stress patterns frozen into the crust from an earlier period of geological activity, and volcanic conduit networks associated with long-extinct magmatic systems. Each of these, if confirmed, would rewrite parts of the Venusian history books. None of them require the more dramatic interpretations that have circulated online, but none of them, notably, have been confirmed either. The data sits in ambiguous territory. The honest answer, for now, is that we do not know what we are looking at. What we do know is that the work is accelerating. Machine learning models are improving. New radar missions are in development. Private companies are beginning to discuss Venus balloon concepts that would deploy instruments in the survivable altitude range of the atmosphere. The planet is getting attention it has not received in decades. The tools that Percival Lowell did not have, and the tools that even Magellan's original analysts did not have, are being built, tested, and pointed at a world that has been keeping its secrets for an exceptionally long time. If those lines are geology, geology is a lot more interesting than we thought. And if they are not, then the story of Venus is going to need a new first chapter. Either way, the second planet from the Sun is not the dead, uninteresting twin the textbooks once described. It is a puzzle, and the first pieces are starting to show through.